Hi everyone, welcome to your talk about the privileged components of the Huawei mobile devices. So I'm Alexandre Adamski and this is Maxime Peterlin. We are the co-founders of Impalabs, which is a French offensive security company, and we are mostly interested in reverse engineering, vulnerability research, and exploitation on mobile devices. So here is the agenda of our talk. After a quick introduction, we'll take a look at the Huawei boot chain. Then we will focus on the security hypervisor. And finally, we will detail the trust zone implementation. So as an introduction, let's see how the Android device architecture has evolved over the years from a security standpoint. In the early days of Android, the kernel was solely responsible for controlling access from user space to the device resources. And for that, it used address space isolation or preemptive multitasking. But the obvious issue with that security model is that the kernel becomes a single point of failure. So if its defenses are breached, then the whole platform is compromised. And that's what motivated OEMs to introduce new security features, such as the security hypervisors that rely on CPU virtualization. So virtualization was originally intended to allow multiple operating systems to execute in parallel, but on the Android devices, it is leveraged to enhance kernel security. And in practice, the security hypervisors, they use the ARM virtualization extension. And these extensions, they define a new privilege level, which is called EL2. They also extend the address translation process. And finally, they allow to intercept various kinds of exceptions. The common purpose of these security hypervisors is to protect at runtime the critical data structures that might be targeted in a kernel exploit. So that would be the kernel page tables, the task credentials, or even the security context. Another security features is the ARM trust zone, and that one consists of a system-wide and hardware enforced separation. So all your software is partitioned into either the untrusted normal world or the trusted secure world. The non-secure software, it is prohibited from accessing the secure resources. And finally, all the communications between the two worlds, they go through a component which is called the secure monitor. Now, when you combine this trust zone technology with a secure boot, that creates a trusted execution environment, or TEE, and those are used from everything from user authentication to mobile payment or content management, which you also know as DRM. Lastly, nowadays, the mobile device, they are securely booted by having each stage cryptographically verify the next one before executing it. And that creates a chain of trust, which has to start somewhere with the root of trust. And that's usually implemented as an immutable component, which is the boot ROM. So if implemented properly, the secure boot makes it impossible to execute unauthorized software on the device. And lastly, the OEMs, they are free to implement additional features, so they can have an anti-rollback mechanism, or do emergency boot over USB, or even boot images encryption. So speaking of OEM, let's now see how the Huawei boot chain is implemented. Their boot chain is divided into 3 stages. So the first 2 are the boot ROM and the X-Loader, and they are executed on a separate low-power processor. And the third stage is fast boot, and like everything after it, it executes on the main application processor. So Huawei devices have obviously a secure boot, but they also do not allow unlocking the bootloader, meaning that you cannot reflash your device partition using fast boot, and you can't run a custom kernel. And also what makes bootstrapping security research even harder on the more recent Huawei devices is that all the critical partitions are encrypted, so you cannot get the plaintext binaries because you can't have custom code running on the device. You're also unable to interact directly with the components that you might be targeting. And finally, they also have exploitation countermeasures, which are implemented in kernel and userland, and one might want to disable that. So on that to say that we needed to find a way to get control over this device's boot chain, which usually entails finding a vulnerability which is also a high entry cost for doing research on those devices. So to give you a little bit of history, the first device we acquired was a P30 Lite with a Kirin 710 chipset. And on this device, the X-Loader, so the second stage, it is signed, but it was not encrypted. So we were able to retrieve the plaintext binary from the firmware updates, and we could start analyzing it. So we managed to find a vulnerability in the implementation of X-Modem, which is the protocol used by the USB recovery feature. In short, the issue was that the payload address, the payload that being sent over USB, its address is not verified, and that gives you an arbitrary write in the X-Loader, and also code execution, because on the boot CPU, all memory is read, write, and executable. The emergency download mode, it can be activated by shorting a test point on the device. That's the pin that's circled in red on our pictures. Shortly after that, we acquired a second research device, this time of the next generation. It was a P40 Lite with a Kirin 810 chipset. Here, the X-Loader is signed and encrypted, but it suffered from the same vulnerability as the P30 Lite. So we could exploit it blindly, which wasn't too difficult because the X-Loader binary was very similar. One interesting difference is that starting from this generation of devices, the decryption key is no longer stored in effusers, so it's only accessible to the crypto engine. And that means that if you want to decrypt firmware images, then you need to use your device as a decryption oracle. And the third and last research device that we got was the P40 Pro with this time a Kirin 990 chipset. And on this device, the X-Loader is signed, encrypted, and it was also not vulnerable. So on this device, we needed another vulnerability to get control over its boot chain. One interesting change is that here, all the critical functionality of fastboot has been moved into a separate component, the BL2, and that is to mitigate potential fastboot vulnerabilities. Thankfully, around 3 months after the start of our research project, the How to Tame Your Unicorn talk was given at Black Hat USA by the TAS Security Labs. And in this talk, they revealed multiple boot ROM and X-Loader bugs, including the X-Loader bug that we had. But among their new vulnerabilities was a boot ROM bug that could be used on the P40 Pro. The gist of this bug is that the payload address is stored in a global variable before it is verified, and that those global variables, they are not reset when the verification fails. So that creates an arbitrary write, like the one we had in X-Loader, that can be used to compromise the boot chain. This vulnerability was also present on the older devices, for which the boot ROM had been dumped, but it needed to be exploited blindly on the P40 Pro. So that's what TAS did, and we really recommend that you read their white paper. It has all the details about this, and it's really excellent research. One last interesting thing is that Huawei fixed the boot ROM bugs by essentially disabling the whole emergency download feature. One last thing is that once we had gotten control over the boot chain and decrypted the boot images, to do any kind of dynamic testing, we still needed to resume execution. And so we do that by, at the boot ROM stage, sending over a patch X-Loader. And so that one is in plain text. So to execute it, we overwrite a return address on the stack. The patches we make to X-Loader, they are to remove the address and size check, also to disable image decryption and signature verification. So once this modified X-Loader is executing, we send over a patch fastboot, and the patches we made to fastboot are to make it think it booted from flash and not from USB, and we'll also continue from there, and ignore any Android verified boot failures. Okay, so once we had gotten our plaintext binaries, we started analyzing them, and the first one we looked into was the security hypervisor. So Huawei's implementation, it is called the Huawei Hypervisor Execution Environment, or HHEE for short. It's similar in purpose to RKP on the Samsung Exynos devices, or to QE on the Qualcomm Snapdragons. The main security feature is that it prevents arbitrary changes to the kernel critical data. So for example, the SE Linux structures, and that even if the kernel is compromised. Another feature is that it keeps a read-only copy of the task credential to detect privilege escalation when the task will next perform a system call or access a file. This hypervisor, it also ensures that only the pages that belong to the kernel code or to the module code, they are the only pages that can be executed at EL1. And another feature is making inaccessible to EL0 and EL1 some physical memory regions that have to do with critical peripherals, such as the modem. So you might be wondering, how is the hypervisor able to enforce all of that? And that is done thanks to a second stage of address translation. So you've got your existing first stage that translates a virtual address into what they now renamed an intermediate physical address. And then there's this new second stage that translates this intermediate physical address into the actual physical address. So this second stage, it needs a second set of page tables, which are under the control of the hypervisor and also allow applying additional memory permissions. And lastly, the hypervisor has its own distinct set of page tables, which control its own virtual memory address space. Now, however, this second stage has some limitations. So if you go into the ARM documentation and you look up the stage 2 descriptors format, you'll notice that there are two fields that can be used to enforce additional permissions. The first one is the XN field, and this one controls whether memory is executable or not at each privilege level. But that's only if a certain feature fit X and X is implemented, and that one was introduced with ARM v8.2. And if it's not implemented, then one of the two bits is reserved to 0, and that means that executability is the same at ER0 and ER1. Now, the second field is the S2AEP, which controls if memory is writable and or readable. And as you can see in its definition, the same permissions, they apply both to EL0 and EL1 accessors. So to recap, because the stage 2 doesn't allow to distinguish between EL0 and EL1, that's why their security hypervisor needs to stay in control of the stage 1 page tables too. And this is done by processing the kernel page tables when they are set initially, and that is when the kernel writes their base address in the TTBR1 EL1 register. So the hypervisor will do a page table walk, and it will carefully check each descriptor. So for example, the descriptors that have the contiguous bit sets, they need to actually point to contiguous physical memory. And also during this process, it will make all of the regular kernel pages non-executable at EL1 and also not accessible at EL0. The hypervisor, it also needs to intercept all the changes that are being made to the kernel page tables, and this is done by making them read-only in the second stage, so that when they are written to, an exception is raised, and the hypervisor can handle it and ensure the modification is allowed. And they also have a clever optimization, I'd say. So if the target permissions, they can be enforced at the table level, so that is using the PXN table and the AP table fields, then they will keep the page writable because it doesn't matter. And also another clever design choices is using the bits 55 to 58 of the stage 2 descriptors. So if you look up in the ARM documentation, those bits are reserved for software use. And that's exactly what they do. They use them to store usage information about the underlying physical memory that this descriptor maps. So for example, they could say in there that this is a kernel page table of level 3, or that this page belongs to kernel code. And then this information can be later used to prevent disallowed changes to protected memory. For example, one change that you wouldn't want is making a kernel read-only page writable again. And the functions that manipulate these attributes, they do a lot of sanity checking to prevent any misuse. So we did a fair amount of reverse engineering work on the security hypervisor, mostly through static analysis, which wasn't too complicated because the binary is self-contained and only has about 300 functions. Yeah. However, there were no symbols and very few log strings. But helpfully, we could find the names and arguments of the HVCs in the kernel sources. With regards to the attack surface, it is composed of the HVC and SMC handlers, also the handlers for the memory faults or for the trap system register accesses, and lastly, any kind of shared memory. So with that, we started looking for vulnerabilities that could be used to compromise the hypervisor, and we actually didn't find any in the exception handlers. However, we did find one in a somewhat unexpected place, which was the logging system. We noticed that in addition to the log buffer's data, its control structure or header was also located in memory that was writable from the kernel. And this structure, this header, it contains various fields. So they have a pointer to the beginning of the data part. They also have an offset within the log buffer where the next log string will be written to. And these values, they are never checked before they are used. So basically, we can ask the hypervisor to write log strings anywhere at any address that is mapped in its address space. However, for exploitation, the log string, it's not user control. But we can exploit the fact that the log buffer is circular. So if we choose a data size of 1 byte, then we'll have each of the characters that will overwrite the previous one, and that will leave only the last character in memory at our target address. In practice, that last character was always a new line, so we could write 0xa anywhere in memory. So with that, and to get code execution, we targeted the linear heap allocator of the hypervisor. It's really simple. The base address and the size of the heap region, they are fixed, and there's only an offset within this region, which is stored in a global variable. In addition, when we looked at the allocation function, we saw that it assumes that this offset is within bounds, and if it's not, then there's an integer underflow, that happens, that you can see on the first line, and the allocator will happily return memory that is outside of the heap region. And thankfully, the memory that immediately follows the heap region, it is both mapped in the hypervisor and also accessible to the kernel, and that is because that's actually the log buffer. So what we did to exploit this and get code execution is that we start by filling up the heap with some stage 2 page tables allocations. And this is done by asking the hypervisor to protect non-existing physical memory ranges. Then we use our write primitive to bump the heap offset right past the end of the heap. So in practice, we just override its least significant byte with 0xa. And now when we trigger one last stage 2 page table allocation, it will be made out of bound and in our kernel accessible region. And now that we've got a writable stage 2 page table, it's basically game over. So what we can do, we can simply change the descriptor in that page table and make their output address span over the hypervisor address range. And we also make the mapping writable. And now we are free to modify the hypervisor code. So for example, we targeted an HVC handler, change its code, and now when we call this HVC, we get code execution in the security hypervisor. So now I'll leave it to Maxime for the next part.
All right, so now let's talk about Huawei's trust zone implementation. So in the introduction, we've explained that ARM trust zone can be used to divide the execution environment into two worlds, the secure world and the normal world. And in this part, we're going to present the different components that exist in each of them, how they work, and how they interact with each other. So first, let's talk about the normal world. So in the normal world, we have Java applications and native processes that are the main users of secure world features. However, because they run in userland, they're not privileged enough to have access to them directly, and they have to go through the kernel. In order to separate privileges, a request coming from userland goes through a certain chain of different components. So first, it is handled by two userland daemons, which are tcd and tauth daemon. Then the request is forwarded to a kernel through a character device, which is called tcns client. And then the kernel receives the input, processes it, and eventually sends it to a secure world through a SMC. it's also important to note that each interface between these components has its own SE Linux interface, which greatly reduces the attack surface in case the device has been compromised. So now let's move on to the secure world. So in the secure world, things can be divided into two main parts, the secure monitor and the trusted OS. And we are first going to talk about the secure monitor. So the secure monitor, which runs at EL3, is the most privileged software component that runs on an ARM device. It performs privileged operations and manages critical hardware peripherals, such as eFuses, power controls, etc. It also acts as a bridge between the normal and secure worlds by forwarding requests between the Android kernel and the trusted OS. Regarding Huawei's implementation, they chose to base it on ATF, which is the ARM Trusted Firmware. It's a reference implementation that is open source and provided by ARM. And Huawei customized this implementation by adding additional groups of SMCs, which are called runtime services. So we mainly focused on the ones that are customs because they are most likely to have been less reviewed than the open source runtime services. So after reviewing the secure monitor, we did eventually find a vulnerability in it. So this one is located in a SMC that is related, SMC handler that is related to the secure element. So when a request is sent to the secure element, the response that is returned uses the user data structure that you can see on the right. And in this structure, the user controls the address of the response metadata. So that's the address of the user data structure itself, and the address of the response data. And this is an address that is stored in the ADDR field of the user data structure. And as you would expect, because both of these addresses are user controlled, there are checks that are enforced to make sure that they are in a specific world shared memory buffer. However, in one of the requests, the check is missing for the address of the user data structure. And in our case, this means that we are able to write the response metadata anywhere we want in the secure monitor's address space. So we can now leverage this primitive to exploit the secure monitor. So we can, so as I said, we can write the response metadata anywhere we want, but we don't control the content of this metadata. We didn't find a way to hijack the execution flow directly using only this, but it does. It allows us to get rid of the check on the response data address. So here, maybe you can see it, maybe you don't, I don't know. But we change the address of the authorized memory region from 0x something to 0xC. And then we have the size that we also change with metadata value, and we replace it to AABBCC55. And with this, we are now able to expand the range of the memory region that is authorized, and we are able to copy the response data anywhere we want. So we don't control this data either, but it gives us more options, and in particular, it allows us to write a single byte of data at an arbitrary location. And we can now use this to hijack a SMC handler and override its least significant byte from 1C to 7C. And now when we call the corresponding SMC, instead of reaching the legitimate handler, we are going to go to an arbitrary call gadget instead. Now we can use this gadget to create stable read and write primitives. And once we have that, to continue the exploits, we are going to double map the secure monitor because WXN is enabled. And to do this, we are first going to locate the page tables of the secure monitor. Then we are going to use our write primitive to add entries into the secure tables that remap the secure monitor as read-write. And finally, from here, we can patch the secure monitor however we like, and we can get code execution from here. So as I said, the secure monitor is the most privileged component on an ARM device. And with this exploit from the kernel, we are able to completely compromise the platform, and we have access to everything in the normal and the secure world. So that's it for the secure monitor. Now we can move on to a trusted OS. So Huawei's trusted OS is based on a microkernel architecture. This is a type of architecture that tries to separate privileges as much as possible. which is why at SEL1 we have a minimalist secure kernel that performs only the critical operations, and all the other features are implemented in userland. So at SEL0 we have the managers, which are privileged processes that are trusted by the secure kernel and that provide the core functionality of the trusted OS. Then we have the tasks and drivers that implement additional OS services. And on top of that, we have the trusted applications that are developed by third parties and by Huawei, and they provide different services to the normal world. So now let's see how the trusted OS is started. So the trusted OS starts its boot process in fastboot, which is going to run the TOS loader, which is found in the TOS binary. Also in the TOS binary, you have a CPIO archive, which contains the secure kernel and the two managers. In the file manager, you have an additional file system, that is the RAMFS, and in this file system, you have tasks and drivers. And now the system manager is going to run the global task from the RAMFS, and the global task is then going to start all the tasks and drivers, and from there we can start loading trusted application, etc., and we can consider the trust zone as up and running. So this gives us a general idea of the different trust zone components, and now we can detail some of them, starting with the secure kernel. So as I said earlier, its main role is to perform low-level operations. It does things such as physical memory allocation, inter-process communication, etc. The idea is to keep it as minimalist as possible. And then we have everything else in userland. And to access the critical features of the OS, we are using syscalls. But these syscalls are mostly restricted to the managers, which we are going to detail later. Regarding security in the secure kernel, one of the most important aspects, in our opinion, is most likely the capability system. So capability-based OS divides privileges in order to provide fine-grained access to kernel resources. Reverse engineering this capability system from Huawei was a bit confusing at first. We didn't really understand what was going on. It took us a bit of time to do. But luckily enough, we also managed to find a 2019 pattern from Huawei in Chinese. So thank you, Google Translate. And it described really the internals of this capability system, which was really helpful. So in Huawei's secure kernel, all the system resources are associated with a capability. On the right side, you can see different types of capability that exist. And these capabilities are owned by a capability node or a C node, and they can also be granted to and revoked from other C nodes. So here's a simplified illustration of what it looks like. Here we have the system manager in the middle with two processes, and we can see that we have different capabilities. For example, we have a thread to represent the access to the main thread of a process, or we have a PMEM that represents the access to a physical memory region of the stack, the heap, the code regions, etc. You also have channels that can be used for communication purposes, etc., etc. And with this, we're now done with SEL1, and we can start talking about SEL0, starting with the managers. So the two managers, HMSys Manager and HM File Manager, are the only two SEL0 processes that are allowed to ask the kernel to perform privileged operations. Also, these are the components where fundamental OS features are implemented, and they can be seen as extensions of the microkernel in userland. And so first we have the File Manager, HM File Manager, which, as its name suggests, manages and exposes two virtual file systems. So we have first RAMFS, which is a file system that is embedded inside the File Manager and that contains the tasks and the drivers binaries. And we have also TAFS, which is a temporary storage for trustlets and libraries. Then we have the System Manager, which implements most of the fundamental features of the OS. It does things like process creation, virtual memory management, etc. And these two managers communicate with other processes through IPCs, and the permissions of the calling processes are checked in the command handlers. Next up, we have the tasks and drivers. And here we'll start with the global task, or a G task. So the G task is the equivalent of the init process on Unix systems, and its main role is to handle normal world commands. And for example, it can register the mailbox and the shared memory buffers so that the normal world can communicate with the trusted applications. It can decrypts, verifies, and loads the trusted applications using different keys that are only accessible by the secure world. It also manages the trusted application sessions, and most importantly, it forwards commands from the normal world to the trusted applications. The other tasks and drivers implement the rest of the OS features and functionalities. We're not going to cover them all in this presentation, but you can get a general idea of what they do with the list that is given here. So for example, we have a driver timer that can be used to create and manage secure timers. Then we have also plat driver that implements different command handler for peripherals, such as the secure element, the crypto engine, the fingerprint sensor. And we also have, for example, the TUI task that can be used to create, to display a user interface accessible only by the secure world. If you're trying to find vulnerabilities in these tasks and drivers, you're mostly going to look into their IPC command handlers. However, the attack surface is greatly reduced by the fact that there are permission checks. So each trusted application has credentials and a security context that can be mapped to privileges, to permissions. When a command is sent through an IPC, the corresponding task or driver is going to check if the trusted application has the necessary permissions. If the trust set is allowed, the command is processed, otherwise nothing happens. So we did find a few vulnerabilities affecting tasks and drivers, but from what we have seen, most of them are pretty secure. We found some heap overflows in the TUI task, as well as memory read-writes, overflows, and leaks in plat driver. All right, and finally, we have the trusted applications. So trusted applications or trustlets are the usernet applications of the secure world. They implement the different services that are needed by the normal world, which is why you can have trusted applications that are developed by third parties and not just by Huawei. They also use the global platform APIs, which is very useful when you do reverse engineering because the global platform standard is very well documented. And generally, these applications are loaded from the normal world. They are loaded from the system and vendor partitions on Android, and sometimes you can even find them directly embedded inside APKs. Trusted applications also come with different settings that are hard-coded in their binary and that influence their behavior, such as single instance, for example, that specifies if one or multiple instances of a trusted can run at a time. Or we have also multi-session that dictates whether one or multiple sessions can be opened. But other than that, the lifecycle of a trustlet is pretty straightforward. So when a trustlet gets loaded, an instance is going to get created. Within this instance, we can open one or multiple sessions. After that, we can start sending commands to the trusted application and wait for a response. And when we are done, we can close the session. And if the trustlet is not marked as keep alive, the instance gets destroyed. Regarding the security of trusted applications, there's a layer of authentication that verifies which non-secure process is trying to communicate with them. So to do this, the trusted applications use information sent by the kernel about these processes. So for APKs, the trusted applications verify the package name and the signing public key. And for binaries, they check the file path, the user ID, and the hash of the code sections. And yeah, as long as the kernel remains uncompromised, and because it authenticates username binaries, we can ensure that the information forwarded to the trustlets is trustworthy. So in their implementations, Huawei made different design choices, some very common but necessary, and others a bit more unique and interesting. So for example, they use secure functions almost everywhere. So this might seem like a small thing, but in practice, you don't see them that often. And from an attacker's point of view, they actually burn a lot of potential bugs. They also copy the buffers they receive from the normal world to prevent time of check, time of use vulnerabilities between the worlds. They also sometimes implement a parcel-based system that is like the one you see in Binder, for example, and it's very useful to prevent memory corruptions because it allows you to handle user data and structures securely. They also implement the usual software mitigations that you would expect in a modern system, for example, NX, railroad, stack cookies, ASLR, etc. Although ASLR used to be bypassable if you had an arbitrary read, because the trusted application base address was written at a fixed location by the loader. And that's pretty much it about the inner workings of trustlets. Now we can move on to what we actually did with them. So obviously, we wanted to find vulnerabilities, which we did mostly through static analysis by reverse engineering their command handlers. So this took us about 6 months to review around 40 trustlets. We also did a little bit of fuzzing using the usual AFL Unicorn Duo. It took a bit of time to get things working, also because of the amount of global platform APIs we had to stub, and also getting things like an elf loader working properly. Our fuzzer is also a bit limited because it is stateless, so we are lacking a bit of depth in the coverage. But it did yield some new bugs that we had not found through static analysis, so it was worth it. On the right, you can see some examples of vulnerabilities we found, and most of them were in third-party trustlets. Trustlets developed by Huawei were relatively clean. So here are some details about 2 vulnerabilities we found in the Keymaster trusted application. So the first one can be used to write user-controlled data in a file of the secure file system, and the second one is a missing check on a parameter type. So this allows us to specify an integer where the program expects an output buffer address, which means that we will be able to copy partially controlled data at an arbitrary address. So to exploit this trustlet, we are first going to construct read and write primitives. For the arbitrary read, we first import an all zeros AES key. We then use this AES key to create a fake key blob that we store in the secure file system using our first vulnerability. Because we control the key blob entirely, we also control the key length and the key offset stored in the key blob. And then by calling cmd-get, we can then use these values to read memory relatively to the key blob address. As you can see in the snippet on the left. And now to perform arbitrary reads, we just need to leak the address of the key blob itself. But it's pretty easy to do because we just have to leak adjacent heap data, and then we can, using the values that are in there, we can infer the address of our object. So now we have everything we need for our arbitrary read. We can use it to break ASLR, as we explained earlier. We do this by reading the base address of a trusted application that is at a fixed address. As for the arbitrary writes, since we partially control the data that is being written, we can simply override function pointers and get code execution from there. And this wraps up this presentation. So all the vulnerabilities that were discussed during this talk have been reported to Huawei and have already been fixed. So even though we did find a relatively good amount of vulnerabilities, so around 160, they mostly affect third-party trusted applications. Huawei's architecture in general is pretty well thought out. They have a lot of defense in-depth measures, which makes exploitation non-trivial or just downright impossible. They separate all privileges and give access only when necessary. They have robust implementations, and all in all, even if mistakes happen, they are mitigated. Apart from that, Huawei relies a lot on binary encryption for their security. So it's true that it makes it harder to find bugs if you don't have the binaries and if you don't have access to them. But it's essentially gatekeeping security research to teams that have the resources to break this encryption layer. And we feel like they're usually not the ones that are incentivized to give you their bugs afterwards. But yeah, that's about it for this presentation. We hope you liked it. We couldn't talk about everything here, but we'll publish blog posts soon that fill the gaps, hopefully before the end of the year. And now we can answer your questions if you have any. Thank you.